Hi, welcome to the fifth video on physics informed neural network. In this video, we shall see some of the procedures to solve one-day linear convection equation using physics informed neural network. So, this is the governing equation for one-dimensional linear convection equation. The beauty of this equation is this will advert the solution. For example, let's say so we have an initial condition like this solution will be moved in this direction over the time. So this equation also can be used to quantify the numerical dissipation and dispersion error. If our scheme is dissipative, for example, let's say we have a Gaussian pulse having amplitude 1. Once we solved using any numerical methods or any schemes, over the time, the amplitude of the wave decreases and is spread over several grid points. This phenomena we call as numerical dissipation. And numerical dispersion is, for example, let's say the Gaussian curve may have multiple wave numbers. If our numerical scheme has some numerical dispersion issues, so this will be spread into different, it will be having several wave number. Different wave number will be propagating at different speed. So because of that, so instead of having a single Gaussian pulse, we have some oscillations around this Gaussian curve. In the previous video, we saw advection equation has some issue when we solve it through numerical methods. So we tested on three numerical schemes. First one is forward in time, backward in space. Second one is forward in time, central in space. Third one is forward in time, forward in space. We observe that when we use the forward in time and backward in space, we are able to get some solution, but the solution is dissipative based on the EFL number we use. But our numerical scheme was completely unstable when we used forward in time, central in space, as well as forward in time and forward in space. From this, we can say that numerical scheme should respect the direction of the propagation. For example, if the wave is moving like this, we should use backward in space. That is, we should calculate the gradient from I minus 1 I. So if we don't use it, it may arise some numerical instabilities. So this we call the directional property or upwinding and those things. So this is quite easy for one-dimensional problem. For example, let's say we have a two-dimensional problem and our wave is propagating in diagonal direction. It's quite difficult to give upwinding because we know upwinding we can give either in x direction or in y direction. But in this case, the wave is moving diagonally. So there are a lot of researches going on, and researchers have come across several procedures for that. Some of the procedures like multi-directional upwinding, rotated Riemann solvers, and those things. So we found that numerical schemes are very sensitive to the characteristic. When we solve Euler equation, we have three characteristics. The three characteristics may travel at different direction. So it's quite difficult to make a biasing based on the direction. So we can't give I minus 1 I, those kind of thing, because each and every wave may be in different directions. So that's the challenging when we want to stabilize these solvers. Now we shall see whether PINN has these kind of issues. These issues are happening because of discretization error. Of course, PINN is not having discretization error. But so before getting it there, we shall see how to solve this equation using PINN. So here we have taken the initial condition. This is the Gaussian curve. So it's always a good practice to non-dimensionalize the equation. The objective of the non-dimensionalization in a physics informed neural network is to make the variable or scale the variable between 0 to 1 or minus 1 to 1. Because optimization algorithm works well if we have the variable between 0 to 1. For example, we know when we solve, so if we substitute this thing here in our governing equation, we will get this equation. So in this test case, we will see whether we get any advantage because of this non-dimensionalization procedure for PINN's equation. Other than that, we also test the effect of the sign of C. For example, whether this PINN is sensitive to the positive moving wave or negative moving wave. So one of the best paper to learn the basics of the PINN is this paper. This is an expert guide to training physics informed neural network. So I would say this is the most comprehensive paper I have seen so far, given a best procedure to solve PINN's equation. A Fourier feature network. This is a good encoding practice, special to another encoding space. And we can also try random weight factorization, which may reduce the computational time. So they have given some best practice to do it. I won't claim all this practice will work for all the problems, but it's always good to try whether it will make sense. So we shall move to Jupyter. We shall open the Jupyter notebook. We shall copy the code to Jupyter notebook. And maybe just we shall run it. And we shall ask it to compare it with analytical solution. Compare the solution with analytical solution at t is equal to 1. Look on this code. And this is a good practice because this ensures the code is consistent every time when we run the code, because the standard PyTorch initialization use a random weight and initialization. You know, the optimization algorithm depends on the initial guess. So in future, we will see some effect of different initialization procedures, because the default initialization followed in PyTorch may not be good for PINNs. 1 or 2 months ago, Gemini 2 is not that much good in generating the code. Now Google has put a lot of effort to improve it. Now it's making pretty good code. So this is a standard neural network configuration that we already went through in our last session. And here we calculate the physics laws. So in this problem, we have two input, that is space and time. So we ensure that we are calculating the gradient here. In the previous example, we don't do it because we no need to calculate the derivative, because that's just a curve fitting. So you can maybe, if you extend the previous curve fitting tutorial to your problem, you can make a neural network that you can call as a surrogate model formed using neural network. So you can find a lot of papers based on that. So this will make a neural network approximation of U. Once that is over, we will calculate the gradient using this function. So here we should ensure we should specify U is calculated with respect to time. That's why we are giving. We should give the independent variable here, U comma U. Then we should specify the size of this tensor. So that is given here. Then we should specify whether we need to create a graph structure. Create graph is equal to true, so that we can calculate the gradient of ux or ut. Similar thing we have done it for space dimension, so that we have calculated du by dt and du by dx. Now we shall calculate the residue of the PDE. So this is the PDE, and if we substitute that, we will be getting the residue. Our objective is to minimize the residue. That's why we are making a square of that, then taking the mean of this. So we should minimize the loss. So we should also minimize the initial condition losses, and that we shall see later. I hope it has written the code for that. So this is training function. This array is to see the convergence curve over the time or iterations. So they have cleverly used that model to calculate the initial condition. So only thing they have done is, so in the model function, if we specify the t is equal to 0, it should give the initial condition. Here they have specified xc, collocation points in the space, and 0 here. They have made 0 with the dimension of xic. Then they calculate the initial loss using this one. After that, they have calculated the PDE loss. So we already went through this function. So here they have given the equal weightage to initial and boundary condition. When the total loss is just a multiplication of these values. After that, we should calculate the gradient of that loss function with respect to parameters. That's what we are doing here. Then it will move to the next iteration. Then we are printing that epochs, initial loss, and a PDE loss and total loss. This command just append that every losses, total losses in the array history. Here we are using our input dimension is 2 because we have two features, that is x and t. So output is 1, number of layers is 4, hidden dimension is hidden, number of neurons in hidden layer is 50. So we have used 10 power minus 3. Anyway, I don't think we need this much iteration. Let's see how much iteration it has completed. Well, it has completed only 5000 iteration. And we shall reduce it to 500. We shall reduce it to 5000. Maybe we shall pause it and again rerun it. So this is the domain, size of the domain. In this problem, our domain size is -5 to 5. And we are simulating from 0 to 1. And here we have taken 500 sample points in the initial conditions. So we know the initial condition curve will be like this. So here we have taken 500 sample points to construct this initial condition. And here, in addition to that, we also need a sample point to calculate the PD residue. So domain will be like this. So let's say this is x-axis and this is t-axis. So we have a domain from -5 to 5 and 0 to 1. So we should generate collocation points throughout the domain where we calculate a PDE loss. So here we have chosen 10,000 collocation points. So that we will pass to this our PINNs function, class. The optimization algorithm that we use is Adams. So in the upcoming videos, we will see some better practices. In this problem, whether we use Adams or any other optimizer will not have big impact. For example, in when we go for complicated full throw problem, we may not get a good solution if we just use the Adam optimizer. We have to use some better optimizer like the LBFGS. I wouldn't say better optimizer. For problem having pins, just a linear optimizer may not be good. In that case, we should go for quasi-linear optimizer, not quasi-linear, quasi-second order optimizer. So if you're interested why this is called first order optimizer and LBGF as the quasi second order optimizer based to open command, I will make a separate video on that. Right now, PyTorch or TensorFlow does not support any second order optimizer. In future, I will make one demo video how to use the second order optimizer here. Anyway, we will not write a second order optimizer from the scratch. We will use the second order optimizer from SkyPy to do that. So this will complete the training and store the losses here. This function we already discussed. And here we are just visualizing the results. We should give the analytical solution. I don't know where it has stored the analytical solution. So here it has stored the analytical solution. So this is expression for analytical. Let's see, sometimes we can't trust all the LLMs. Minus 10 numpy minus c into 10 square. Yes, perfect. So it has calculated analytical solution only at the time t is equal to 1. Fine, anyway, we asked it to compare only at time t is equal to 1. So let's see whether it has completed the solution. At t is equal to 1, it has moved here. Fine. Anyway, this is matching. And where PINN has a good solution. Now we shall check the first objective, whether PINN is sensitive to the direction of the velocity or direction of the characteristic direction of the flow. So for this, we should set the C to -1. And we should also correct the analytical solution. Of course, we can also auth that when we do it, we will get the analytical solution like this at x is equal to this one. So the problem is more or less fine. Previous video, we saw the solution of that numerical method is very sensitive to the amplitude of the initial condition. Maybe we shall give a prompt to this Google Gemini to change the IC. So now we have increased the complexity of the IC. It's taking very long time, so I will reduce the number of neurons. Now we shall run the code. It has completed the solution with 30 neurons. Even with that 30 neurons, you can notice it has made a pretty good approximation. That's the beauty of physics in computer data. So when we go for high wave number and those kind of stuff or stiff equations, if we make a good pin configuration, that can be able to outperform the traditional methods. So here it took around 2 minutes. Of course, traditional methods may not take this much time, but to get this accuracy, uh, traditional methods need even more collocation points what we used for PINN. That's the beauty of PINN. In the next video, we shall make a better comparison between physical neural network and traditional methods for a given error. So now we shall see the effect of the non-dimensionalization parameter on this equation. Now we shall ask this Gemini to a number of epochs to 5,000. So let it complete the process. The beauty of this one is it will show how to non-dimensionalize every parameters and what are the non-dimensional scales it has used. So it's non-dimensional length by LC and time with TC. T is the end time. U with UZ. UZ is maximum value of this Gaussian pulse. For this, that is around 1. Maybe we shall paste it here and run. I hope it has given the right code. Anyway, we shall have one small look. So here it won't make any mistakes. Fine. This is also fine. Oh, we already saw this is standard. So now it has changed the domain to -1 to 2. Anyway, it's a right moving wave, so this is okay, not a big deal. Now we shall see characteristic. So LZ is equal to 1 divided by square root of beta. So it's also not it's also considering the effect of the beta here. This may not, I'm not sure whether this is required. Anyway, let it be, because if it scale back to original value, that won't make any problem. So TC is equal to LC divided by C. Okay, fine. And UC is equal to 1. X is non-dimensional using T and T is non-dimensional using TC. So it has completed the simulation. Both of them give more or less same result. But the solution of non-dimensional spin is slightly poor than actual pin, basic pin. So in this case, the basic pin outperform the non-dimensional spin. But in some of the cases, if we have some convergence issue, non-dimensional spin is the only choice. So I hope in this video you got an idea what are the advantages we'll be getting when we solve the problem using PIN. So first of all, we no need any separate architecture or does not care about discretization. But in traditional methods, we need upwinding to solve hyperbolic equation. But when we solve using PIN, we no need that those upwinding and those. It can take it. It can handle both right moving wave as well as left moving wave without any special care. One of the biggest challenges with PIN is it is computationally very expensive when compared to traditional methods. In the upcoming videos, we will see some of the procedures to reduce the computational cost, and we shall make a head-on comparison between traditional methods and PIN. I hope you enjoyed this today's video. I will see you in the next video. Thank you for watching.